class, Mr. York here. As you know, it's a weird week, and I wanted to talk with you guys about projectile motion this week. But because of the schedule, I think I'm going to need to record a video. So, if you guys can see, I've ridden my bike out here to the Belmont Harbor Archery Range, which I didn't even know existed, but it's actually quite lovely. It's a big open green space right next to the lake. It's a little overcast. I think the weather calls for rain, so I'm going to try to do this quickly. So the reason that we're here is that I want to start showing you guys projectile motion. We have a project coming up at the end of the month in which we're going to make projectile launchers, so I feel like it's only fair that I show you how they work early on. So you can probably see these pencils sticking out of my shirt, and we are going to use these as our projectiles today. They're pencils with a little bit of fletching on the back and those like big chunky erasers on the tip. So, in order to fire them, I've rigged something up. Here, I can show you. Can you see that? There you go. This is a miniature crossbow that I made last year during remote learning. It's like just over a foot long, and it fires these specialized projectiles, which are pencils with chunky erasers on them. And I have it mounted to this board, and to the board I've also mounted an old-timey protractor. It's like maybe a bevel gauge. I don't know what they're exactly called. But this is going to allow us to change the angle that we launch our projectiles at and keep it really accurate and consistent. Like right now I can see that I'm exactly at 32 degrees. So it's pretty accurate. The way this is going to work is I'm going to launch one projectile at 60 degrees, one projectile at 45 degrees, one at 30 degrees, and then one at 15 degrees. And we'll see how that affects the distance that they go. I should say, I think last year we measured that this projectile launcher launches pencils at almost exactly 17 meters per second. I'll double check that at the end. And I might do that just by launching it straight upwards and measuring the time that it takes to come back down. Because I can do that and find the initial velocity. But without further ado, let's get started. I'm going to start by setting this at 60 degrees, which is here. And we will launch the projectile. Oh, can you even see that? Yeah, kind of. We'll turn this around. All right, 60 degrees, projectile number one. In 3, 2, 1. Okay, there it goes, and hit the ground. I'll measure these all afterwards. Projectile number 2 at 45 degrees. I guess it's going to be the green eraser. Let's set this for 45 degrees. 45, there we go. And launch in 3, 2, 1. Oop, you see that? Went a bit farther. Uh, 30 degrees will be our pink eraser. Let's lower this down to 30 degrees. 1 second. There we are, 30 degrees. And we'll launch in 3. Well, let me tilt you up so you can see better. 2, 1. You see that? Landed somewhere over there. And then the last one at 15 degrees will probably be the shortest launch of all. Let's set this down to 15 degrees. Is that 15 degrees? That's 15 degrees. Pretty low. And we will launch that. Well, I don't even need to hold it in place. Let's see if I can give you a better angle of this. Oops. We're tilted. We're gonna launch in 3, 2, 1. Whoops. Misfire. We'll try that again. Stick it right here. And launch in 3. Oops. There, can you see now? Yeah. 2, 1. There it goes. I'll measure those and I'll get right back to you. Okay, and lastly, let's do a shot with it at exactly 90 degrees. That way, we can track how long it takes to go up and then back down and figure out, using kinematics, what the initial velocity of this was. Just to double check my measurements from last year. So, I'm gonna put the camera down for a second. I'll try to pick it up again so you guys can see it land, but actually it's gonna be important for me too because I'm gonna have to count the frames. So 1 second. Let's set this, there. Sorry, that's as good as it's gonna get for now. All right, and 3, 2, 1. Okay, I think that was pretty good. I'll try to figure out how long that took. Hey class, I'm back inside. It is pouring rain outside, so now is as good a time as any to walk you through what we just did, and then also to figure some new things out. So to start, we did 5 different launches. The first one was at 60 degrees. It was really kind of high. The second one was at 45 degrees, which went farther. The third one was at 30 degrees. And the last one was at 15 degrees. Oh wait, that's only 4. The last one was at 90 degrees, straight up and straight down. And I did this one so that I could double check the initial velocity of my pencil bow. The initial velocity that I had at first, this is from last year, was I think around 17 meters per second. So we can double check that. And I just got done counting the frames in the video that it took to go up and down. Those are like video frames. That's like how many still pictures my camera took. And it was 87 frames. And I just checked, and my camera that I'm actually using right now shoots at 30 frames per second. So I can actually convert this number of frames into a time knowing this conversion factor. So let's just do that real fast. 87 frames times my conversion factor, which is 30 frames for every 1 second. So I just need to divide 87 by 30, which is easy, got that. 87 divided by 30, and that gives me 2.9 seconds. So that was the total time it took the pencil to fly up and then back down. If I want to find the initial velocity, it'd be easier for me to just look at the time that it takes to go up to to its maximum height, because then I know that the final velocity would be 0. So let's try that. I'm going to look at half of this, which is half of 2.9 is 1.45. So my delta t is going to be 1.45 seconds. Let me just draw a picture so I know what I'm talking about. That's 1.45 seconds to go from the ground to the top. What else do I know? Acceleration is negative 9.8 meters per second squared. My initial velocity, oh no, I don't know my initial velocity. My final velocity is 0 meters per second, and then my initial velocity, that's the thing I need. So I need an equation that can give me this if I know final velocity, acceleration, and time. So that's going to be this one, the first one. Vf equals Vi plus A delta t. This is 0, so I can just rearrange this to be negative Vi is equal to A delta t. I can plug in now. I mean, if I want to. I could also, let's just simplify one more time. So Vi is negative A delta t. That's easier. So let's plug in negative A. So that's negative 9.8 meters per second squared times the time, which is 1.45 seconds. 1.45 seconds is going to be my initial velocity. Let me do that on my calculator. And that gives me an initial velocity of 14.2 meters per second. It's not quite as fast as I thought. Not quite as fast as it was last year. But, you know, this is homemade, and it's been sitting around unused for a year, so maybe 14.2 is just fine. So when we do the kinematic equations later on for all these different flights, we know that the initial velocity, since the pencil's the same and the bow is the same, the initial velocity is going to be 14.2 meters per second for all 4 of these. And I'll grab a fresh piece of paper and we'll do the kinematics for these 4 launches. Okay, I've got a new piece of paper here and I found my protractors. So I actually drew our 60-degree angle really accurately because this is the first projectile launch that we're going to talk about. I mean, the rest are just going to be the same, so I might not even go through all of them. But if we're going to look at this launch, I think the one thing that's important to remember is that our initial velocity is going to be the same as all the others, just because I can't change how fast the pencil bow shoots at. So that's going to be 14.2 meters per second, just like all the others. Oh, and for comparison, I measured how far it went. Where did that go? Here? Okay, I measured how far it went, and the 60-degree angle went approximately 18 meters. So that's our measured value. So that's kind of going to give us like a point of comparison once we actually find the range using kinematics. So just to reiterate, what we're trying to find now is the total distance that a projectile shot this fast at this angle should go. And it doesn't truly matter what the projectile is. It could be a baseball, could be anything. In this case, it just happens to be a pencil, but it could be anything. So it's going to follow this parabola, kind of like this. We have all the information about its like initial state, but what we want to find out is the range. What is delta x? In order to do that, we need to find out what the components are. So let's just find the components real fast. Remember, that's Vx and Vy. Vy is going to be the velocity, or the magnitude of the vector, times the sine of this angle. So give me a second. What was that, 14.2? 14.2 times the sine of 60 degrees. And I don't know if you can read that. That gave me 12.3. 12.3 meters per second. And I'll do the same for the x component, except this is going to be the magnitude times the cosine of this angle. So 14.2 times cosine of 60 degrees, and I got 7.1 meters per second. Now, since there's no acceleration in the x direction, if I knew the amount of time that the projectile took to go from beginning to end, I could just multiply that by 7.1, and that would give me the distance. Unfortunately, I don't have this, and I can't just assume that it's going to be the same as when we shot the arrow straight up and back down. This is fired at a different angle. Its vertical velocity is different. It's just not going to stay up in the air as long. So I need to find this new time. And I think the best way to do that is to do our trick with like using half of the time that it takes to go up and then back down. And we can do this because we have the vertical component of the velocity. That's just how fast it's going up. And if I know how fast it's going up, I can figure out how long it'll take to go away from the ground, turn around, and come back down. So let's do that. If I am looking for this amount of time, this amount of time right here, delta t, I can assume that the final velocity is 0. The initial velocity is going to be 12.3 meters per second, and the acceleration is negative 9.8 meters per second squared. So let's do that. I'm going to use the first equation, which is final velocity is equal to initial velocity plus a delta t. I can rearrange this. Well, I'm trying to solve for delta t. So I know this is 0. That's easy. Then I can subtract this on the other side. So negative vi is equal to a delta t. And then what? I just divide both sides by a. Negative vi over a is equal to delta t. So if I plug in, that'll be negative 12.3 meters per second over negative 9.8 meters per second squared, and that should give me something in seconds. Give me 1 second. One moment. 12.3 divided by 9.8, and that gives me 1.26, let's say. 1.26 seconds. So that is the amount of time that it takes to go up. Not the amount of time that it takes to go all the way. That's just the amount of time that it takes to go from here up to the top. So in order to find the total time, I just need to multiply that by 2 to reach the ground. And that'll be times 2, 2.5 seconds. I realize that 1.26 times 2 is not 2.5. I just didn't round the number on my calculator, so this is the new unrounded number. So 2.5 seconds is the amount of time that it takes to go all the way to the ground. Because I know that, and I know how fast it's moving in the horizontal direction, now I can find the total range of this shot. So remember, velocity is displacement over time, or in this case, distance is velocity times time. I can just plug in my horizontal velocity and the time, and I'll find the range. So my horizontal velocity is 7.1 meters per second, and my time is 2.5 seconds. So this whole thing is 2.5 seconds. And my range is 17.75 meters. Oh, and that is actually really close to my measured value. So that tells me that my initial velocity that I calculated is probably pretty close to right. So hopefully this helped. I think I'll do one more after this on another clean sheet of paper, and hopefully that will at least give you a good start into how we use kinematics to solve projectile motion problems. Okay, welcome back. Let's see that? So I have here an angle of 45 degrees. This is going to represent our second shot that was at this angle. And again, I want to figure out how far, theoretically, something shot at this angle and with an initial velocity of 14.2 meters per second should go. The actual distance that I measured, let me just write this, measured out in the field was about 22 meters. Just like a point of comparison for later on to see how close we were. And the way that we are going to solve this is going to be the same as the last problem. We need to know how fast it's moving, how fast our projectile is moving in the x direction. So that's the x component of the velocity. And we also need to know how long it takes to fly through the air. If we know those two things, we can figure out how far it goes, the total displacement in the x direction. So that's what we're aiming for. We're trying to figure out what the total distance is that our projectile goes. In order to do that, we need components. So let's find the y. Again, that's just the velocity, or the magnitude of this vector, times the sine of the angle. So 14.2 times the sine of 45 degrees. And I got 10.04. Let's just say like 10.0. I like that. Meters per second. And just an interesting factoid for you guys. When you find the x component of something that's at a 45 degree angle, it'll be exactly the same number. Let's just to show you. 14.2 times cosine of 45. And look, I got exactly the same number. 10.0 meters per second. That's only true for 45 degree angles, but it's kind of interesting. Now we're ready to find the time. We know how fast it's going in the x direction, which is part of what we need. Now I need to know the time, the total time that it takes. And I'm going to do the same thing. I'm going to, instead of just trying to find the whole time in one go, I'm just going to find the time that it takes to go from its lowest point to its highest point. That's what I'm going to try to find. And in order to do that, I'm just going to look at stuff happening in the y direction. So my initial velocity in the y direction is 10 meters per second. My final velocity in the y direction is 0 meters per second. And the acceleration in the y direction is negative 9.8 meters per second squared. Now what I don't know is the time. That's what I'm going to be finding out. So let's use that same equation. Let's see. V final, I could write it correctly this time. V final in the y direction, so Vfy, is equal to the initial velocity in the y direction plus a, so acceleration in the y direction, times delta t. There's no x and y difference in time, because it's actually the same for both. I can rearrange this. That's 0. This negative VIY equals AY delta t. You guys see that? Yeah. I'm going to divide both sides by the acceleration. So negative VIY over A is delta t. And now I can plug in. Negative 10 meters per second over negative 9.8 meters per second squared. That is going to leave me with an answer in seconds. And what is the answer to that? Well, it's almost 10 divided by 10, so it's probably going to be pretty close to 1 second. But let's find it out. 10 divided by 9.8. Yeah, basically it's 1 second. Ooh, should I just write 1? Yeah, 1. That rounds down to what? 1 second. Now, remember, that's the time that it takes to go from the lowest point to its highest point. In order to find the total time, I need to double it. Oh, you couldn't even see what I was drawing up there. I need to double this time in order to find the time for the entire trip. So let's do that. Times 2, that gives me 2 seconds. So when I use the horizontal component of the velocity and the time to calculate the displacement, I'm going to use this time, 2 seconds. So the x component of the velocity times this time will give me the displacement. I need to plug those in. 10 meters per second times 2 seconds equals, well, I don't need to grab my calculator. 20 meters. And oh yeah, let's see how that compares to our measured value, which was 22 meters. It's really close. The difference, if you're wondering like why there's a difference at all, why it's not perfect, it's probably because there was a little bit of error associated with me measuring the initial velocity when I fired it straight up. Also, I don't know if you noticed, I had to kind of hold my finger on the pencil to make sure it didn't fall off, so maybe a little extra drag there. But otherwise, I hope that made sense. I want to say one thing about 45 degrees. It's a bit special because 45 degrees, as you noticed, it flew farther than 60 degrees. 45 degrees will always fly farther than any other angle. And the reason for that is that at 45 degrees, you have the maximum value for the horizontal component of the velocity and the maximum value for delta t, which depends on the vertical velocity. So it's kind of maximizing the product of these two. That might seem confusing, but I can explain that in better detail later on. But the point is that 45 degree angles always shoot the farthest. Okay, I hope that helped, guys. I will see you in class, and have a great week.